Hello, students. Let me go back here a second. So, um, I know this is labeled in these slides I'm showing you. It was labeled last problem. This is question 5 in your homework. And I'm going to go over it in some detail because I understand that these questions can be a little difficult. And I also want to introduce a new concept here. This also will work with question 6, what I'm going to talk about. But I don't want you to be like, oh, I can just apply this everywhere. Um, we're going to talk about an elastic collision. Right. So remember that with elastic collisions, the momentum is conserved and the kinetic energy is conserved. There's no loss. There's no work done to change the system in some way. There's just the objects bounce, and that's it. So we have this problem. We're going to let a block slide down a ramp that has some arbitrary shape, so we can't do anything clever like look at forces. And we have to look at the energy here. But it's going to slide down this ramp, and it's going to hit block B, and it's going to come back. All right, so the dotted box A is going to be its final position, which obviously it doesn't return because what happened is B is at rest, and A has all the energy to start with, and it gives some kinetic energy to B, so it can't go back where it was. So the problem is asking, essentially, it's asking how high does A get to? But to get that, you also need to basically figure out what the energy is that B gets. So you need to figure out what the velocity that B has. And so that's where the momentum comes in, is we got to figure out what happens in the collision. So, like I said, it's both an energy and a momentum problem. A meets B, some of A's momentum and some of A's energy is transferred to B. So any sort of momentum problem, we can work through, but let's start with the energy. Block A starts with potential energy, U is mgh, and when it gets to block B, that potential energy is all turned to kinetic energy. So we can just solve, right? If it starts, let's actually go back. It starts 5 meters up on the ramp. So in your text, in your problems, you obviously have some different numbers here on these different blocks. And I just picked some random ones. That's nice. Actually, I did this 2 years ago. But everyone should have the 5 meters as a common distance that falls. Everyone should get the same velocity when we go through. Right? As V is going to be square root 2gh. And we're going to use G as 10 throughout. For the homework, you should use 9.8. But I don't actually think it'll affect very much. Anyway, so you get a velocity is 10 meters per second. Note, we're saying here that it's velocity of A initial. All right, so that's why we have so many subscripts. We're trying to keep track of initial and final velocities of multiple things. So just from the energy stuff, we get what we expect, is V is 10 meters a second. Then we talk about the collision. What we're going to say is that the momentum before the collision equals the momentum after the collision. And so we just write out P for the momentum before and after, and then what those are, M times V for each. And then we plug in what we know. B is at rest. It doesn't have momentum. A is the thing's moving. Its momentum is 50 kilogram meter per second. Now, on the other side, we don't know any of the momentums. That's a problem. That's like the bowling pin problem where I realized I didn't give you a final velocity somewhere to solve things. Well, I still haven't given you one here. That's where this kinetic energy, when you're told that something bounces elastically, you can conserve kinetic energy. So kinetic energy on the left equals kinetic energy on the right. Well, block B isn't moving initially, all of that energy is on the block A, and it has 250 joules. Now, what happened here is in these notes, I've canceled out the common 1/2 because it's on all the terms to it. So we have a system of equations. The top equation is 50 kilogram meter per second is 5 kilograms VA final plus 9 kilograms VB final. And then the next one is 500 joules is 5 kilograms VA final squared plus 9 kilograms VB final squared. If you remember, I gave you in the very first lab a problem where you had to solve a system of equations with a quadratic in it. And this is where it comes back up. And this is an ugly system. It's a solvable one, but it's ugly. And I go through solving it in these notes. All right, we simplify everything down because we know the units will come out to meters per second. And what we have is 500 is 5x squared plus 9y squared, and 50 is 5x plus 9y. Solve equation 2 because that's the simplest one. Plug into equation 1 and you get a quadratic. And, so here we're doing the math. We square x that we plugged in, and then we multiply by 5 and divided by 5. And, we simplified everything out. And you get a term, and then you solve for that term. All right, it's a quadratic. One obvious solution is y is 0. So let me discuss that for a minute. When you're dealing with momentum and energy together and you get a solution, if one of them gives you the velocity it had in the beginning, then the collision didn't happen. Right? Is block B was at rest. If block B stays at rest, then the collision never happened. So you have to take the other solution. All right. So we solve for y, and then we use that to get the actual velocity for block A, and lo and behold, it goes backwards. All right. And it's not as fast as it came in. It came in at 10 meters per second, and it goes out at minus 2.18. And then we use the energy arguments that we did before to get how far it goes up, and it goes up 0.4 of a meter. So that's a long problem here, right? We did a lot. Right, so here's where we started. I fully expect that to be like 2 or 3 sheets of paper, easily. Right, that's a lot of work. So there must be an easier way to deal with this, right? I mean, these inelastic collisions were a lot easier, and there was, always a trick to get around some other stuff. Is there one here? So this is where I want to introduce a concept called the center of mass. Right. So I'm 8 minutes into the video. That's good. 8. So when we talk about a system, but we don't talk about where it is. All right. We kind of talk about where each object in the system is or how they're moving. But we can talk about an average location for the entire system. And that's what we call the center of mass. And it's a weighted average, right? If you remember statistics, you did weighted averages at some point, surely. Here, we weight it with the actual masses of the objects. Right? So if we're talking about the truck and the bug, then the truck has most of the mass, so the center of mass is going to be somewhere near the truck and away from the bug, at least until they collide. So the center of mass is just a theoretical point. It doesn't actually belong to either object. It belongs to the system, and it can be outside of either object. I mean, if they're the same, if these things are the same masses, then the center of mass is just between the two objects. Now, this point, though, can move, and we can define its velocity, and we're effectively taking the derivative of the center of mass, and it just distributes the derivative onto each thing's position. And you can calculate an acceleration for the center of mass the same way. So here, when we calculate the velocity, well, the things on the top row are all momentums. In fact, that's the total momentum of the system. The center of mass of an object is the total momentum divided by the total mass. Isn't that nice? Right. So you can do the acceleration, and the punchline here is the acceleration of the center of mass. You take a derivative of the velocity, and that takes a derivative of all the interior, v1 and v2. That's really just a derivative of the total momentum, which is the net force. All right, so the acceleration would be the net force divided by the mass, which makes sense. All right, that's why we treat big objects as not individual tiny, we treat them like individual tiny particles because all the particles in a big object share a common center of mass effectively. But why do we bother with it? Well, because mass is usually conserved and momentum is definitely conserved. The center of mass velocity is constant if there's no external forces. If there is, then that acceleration tells you what the external force is. The explosions and the inelastic collisions problem all have already dealt with center of mass. The stuck together mass is at the center of mass, and so they move together. And then this is the clever bit. The problem we just did can be done again. I talked about in previous videos the common problem of talking about a boat crossing a river. And the idea is that velocities are relative. You always measure a velocity relative to something you think is not moving. All right, and note I said think is not moving. It may very well be moving, but you can measure relative to anything that you can pretend is not moving. So we can measure things relative to the center of mass. And that's going to let us solve a simpler problem. So I go through this in these slides. And we'll also use center of mass in other places when we talk about rotation eventually. So going back to this elastic collision we were doing, your general conservation equations look like this. Right? You have momentum conservation and energy conservation, kinetic energy conservation. So we can kind of write these things differently, right? We write it out in terms of mass and velocity, but we can also write it we can write the kinetic energy in terms of momentum as well if we want to, right? But what do we mean when we talk about writing in terms of relative to the center of mass? It means we're kind of adding velocities up, right? So we can use basically a new set of coordinates, right? When you do a problem, you draw out your coordinates and you're measuring everything relative to the origin. Well, draw a new one that's at the center of mass and moves with the center of mass. And it'll have these little tick marks on it. VA tick mark, or VA prime, is the velocity of A minus the center of mass velocity, and the same with B. And we're just adding the velocities up. Or in this case, we're subtracting the velocities. So if we do that, if we do this sort of change, going from the piece of paper coordinate system to the center of mass coordinate system, or from the laboratory to the center of mass system, what we find is that the total momentum is zero. That's a very weird statement. If we measure everything relative to the center of mass, there is no momentum. Now, each individual object has momentum. We can identify it. It's mass A times VA and mass B times VB. But the totals, they disappear. So we can use that information. Right. So what we mean is, when we talk about the center of mass frame, it's the we're talking about a frame, we're talking about a coordinate system. We're talking about how we measure distances and velocities. And so this frame is the one that represents zero total momentum. Now, someone somewhere else will see a different momentum, right? Because these velocities are relative, so the mass times velocity is relative. What matters is the changes in them. So we can change our coordinate systems, and that's what we're doing. And in this case, the left side, the momentum 0, so is the right side. But we don't make at 0 because we actually want to solve something about that. All right, people keep texting me for some reason. So we can work through a bunch of stuff, right? The kinetic energy we can write in terms of the momentum. Basically, I gave you that in the first lab. 1/2 mv squared is basically quantity m times v squared over 2m, or p squared over 2m. So we eventually get a set of equations. Come on, go forwards. Right. So we can solve this system, and I invite you to work through it. But the punchline is the square of the momentum of block A is constant in this center of mass frame. Now, one version of that is that it never collides, it just keeps going. And the other version is that it reflects. It starts out with a velocity relative to the center of mass, and it comes in with that velocity, and it leaves out 180 degrees opposite, but with the same amount of velocity relative to the center of mass. And at the moment the thing collides, it's at the center of mass. So we can use that. So that gives you a recipe for dealing with elastic collisions in a simpler way, is you find the center of mass velocity and convert all of your velocities to center of mass related velocities. And you check that the total momentum is 0. All right, that's important. Check that you did the conversion correctly. Change the directions, change the signs and the velocities, and then convert back. Undo the change you did. And in 1D, that works. Now, for all other sorts of elastic collisions in higher dimensions, all right, we talk about cars colliding and bouncing off each other at angles, you have to have more information. But in 1D, that solves the problem. So we can go through this in terms of the center of mass and see if we get the same answers. All right. So first, we carry over the block A's velocity, and that's 10 meters per second. Block B is 0. And so the center of mass is the total momentum over the total mass. And that gives you this 50 divided by 14 is about 3 and 3.6, roughly. And so we find new velocities relative to the center of mass. Okay. And what's happening is, as block A moves, it's catching up, it's getting closer to the center of mass, and so is block B. Even though it's a rest relative to block A, relative to the center of mass, it's moving because the center of mass is moving. It has a velocity. Right? So what I would recommend is sketch it out. Say once, draw something out where there's some distance apart, and then 1 second later, leave the center of mass in place, and you see that, so you do several drawings from the point of view of the center of mass at rest and then block B at rest, and you'll see it make sense. So before the collision, we have these velocities relative to the center of mass. Afterwards, we flip the signs, and then we go backwards. We convert back, and what we get is block A moves at this 2.85 meters a second that we found before. we didn't have to go through and solve that ugly equation, in the sense that we solved it once, found the recipe, and then we apply it over and over again. So we didn't have to do quadratic algebra because we converted to a place where the quadratic equation was easier to deal with. And then you do the same energy stuff, you get the same answer there. And that's the center of mass introduction and this horrible problem. And the center of mass stuff will work with number 6 as well. So number 6, we have a tennis ball and it's bouncing it's going to sit on the top of a basketball, and when they collide, what's going to happen is the basketball hits the ground, it's going to immediately change direction. It's going to bounce upwards. And then so they're effectively, the tennis ball and the basketball are going to collide immediately. And then we figure out how, right? So part A is doable with energy. Part B is an elastic collision you have to do with momentum. But what you get out of that is, if you've ever seen this demo, and I'll have to show it to you if I can find a basketball that's inflated in this school, is the tennis ball goes flying off, right? Because the momentum of the basketball, which is much heavier, is all basically transferred to the tennis ball. Right, so that's going to conclude this video. We'll do some two-dimensional stuff and some other problems, and we'll see where we are.